Hi, so this is the second part of how to use the rules of differentiation. Namely, we're going to look at how to apply the power rule. Okay, so in the first example, they want us to find f prime of x if f of x is equals to 4x minus 3 everything squared, right? So don't make the mistake of simply applying the power rule to this like straightforward as it is, because you are seeing that exponent of 2, all right? Notice that inside of your bracket, right, your function is more complex than just simply an x. You are dealing with a 4x minus 3, right? And we know from basic algebra that when we have a bracket squared like this, this is not equals to, right? It's not equals to 4x squared minus 3 squared, right? That is not true, right? So what do we do when we have a bracket squared like that? Well, we basically write out the bracket out twice, so we have the same bracket multiplied by itself. Okay, so you're going to open a bracket, 4x minus 3, close bracket, open another bracket, 4x minus 3, close bracket, right? And notice that this is still f of x, all right? We haven't taken the derivative yet, so you don't write down the notation of the derivative. Okay, then we just simply FOIL this out, so we'll have f of x is equals to 16x squared minus 12x minus 12x plus 9. Okay, right, now we are able to combine the two like terms of minus 12x, giving us f of x is equals to 16x squared minus 24x plus 9. Okay, now all our terms are in terms of just a coefficient times x to some exponent, right? And once we have our terms in that form, we have the right conditions to apply the power rule. Okay, so let's go. So we're going to have 16 times 2, right, which is 32, right? And we subtract 1 from the exponent, so 2 minus 1 is 1, okay? Minus 24x, x has an exponent of 1, so we have minus 24 times 1, which is minus 24, okay? And the exponent of 1 minus 1 is going to be 0, and anything to the exponent 0 is 1, okay? The constant term of just a 9 is just going to fall away, because remember, the derivative of a constant term is 0, okay? And there you go. So that is f prime of x, 32x minus 24. Okay, now let's go on to the next example. They say find dx of the product 2x minus 3 times x plus 4. Right, now remember I pointed out to you in the previous video that when they give you a product like this, it's sometimes a way for them to try and trick you. A lot of students will say that this is equals to dx of the bracket 2x minus 3 times dx of the bracket x plus 4, right? This is again not true, right? This is not how you are going to find the derivative of a product, right? Again, this is just basically going back, same thing as what we had in the first example. We have to FOIL out those two brackets, right? We haven't taken the derivative yet, so with this notation, right, if you take it back to general form, this is dx of some function y, right? So we're going to start off by saying let y equal, okay, 2x minus 3 times x plus 4, right? This is going to allow us to FOIL out our brackets, right? Because if we FOIL it out inside of the dx operator, we are kind of saying that we are already taking the derivative. So let's not confuse ourselves. Let's pull out our function, right, and call it y and manipulate it on the outside. Okay, so we'll have that y is equals to 2x squared plus 8x, right, minus 3x minus 12. Okay, so then this is going to give us 2x squared, 8x minus 3x is a positive 5x, right, minus 12. Okay, then we can take this back into our differential operator dx, right, of the function 2x squared plus 5x minus 12, right. Now we see that everything is in proper condition of a coefficient times x to some exponent. So now we can say simply equals, because we are taking the derivative now, this is equals to 4x, right, plus 5. Okay, and that's it. Right, then the next example is talking about, again, we have the dx operator, dx of the cube root of x plus 1 over the square root of x, right, and all of that is in one bracket. Okay, so we'll start off again. We're going to say let y equal the cube root of x plus 1 over the square root of x. Okay, now once we have this, we just basically have to manipulate our radicals, and we know that from the laws of surds, right, when you have something like the m root, right, of a, okay, this is the same as a to the exponent 1 over m. Okay, so that radical, right, comes up and picks up the exponent that is on your variable on the inside. Okay, so it comes in from underneath, right, and it becomes the denominator of whatever your exponent is of your variable on inside. Okay, so that's exactly how we are going to manipulate this situation. So we're going to have y is equals to, right, so we're going to have x to the exponent 1/3, right, plus 1 over x to the half, right. Now, so that we can apply the power rule, we can bring that term of x to the exponent a half to the top, right, which will change its exponent from a positive to a negative value, right. So we'll have x to the 1/3, right, plus x to the negative a half, right. Now we have two terms which are being added to each other, right. In your head, you can call your first term a function g, and the second term a function p, maybe. And basically, we're going back to the rule that we say that if we have a sum or difference of functions, right, then the derivative of the full function is just the derivative of each component, right. So it's still just the power rule. So all that means that we're going to apply the power rule to the first term and the second term individually. Okay, so now we are able to say, okay, you can put it back in the dx operator. So dx of x to the exponent 1/3 plus x to the exponent a half, right, this is equals to 1/3 times x to the exponent 1/3 minus 1. Okay, this is plus minus a half, okay, times x to the exponent minus a half minus 1. Okay, then when we simplify this, right, we are going to have, and 1/3 minus 1 is minus 2 over 3. Okay, then we have minus a half times x, we have minus 1/2 minus 1 as our new exponent, which is minus 3 over 2. Okay, so then we can just clean this up. We can't leave our exponents as negative exponents, remember. It's just nice to leave them as positive exponents, right. So first things first, a negative exponent indicates division, so we'll have 1 over 3, right, times x to the 2 over 3, okay, minus, okay, 1 over 2 times x to the exponent 3 over 2, right. And now we can just put this back into radical form. All right, so this was going to be 3 times the cube root, right, of x squared. Okay, and this is minus 1 over 2 times the square root, right, of x cubed. Right, and that is your derivative function. Okay, going on to the last example, right, we have the question, what is dy by dx, right, if y is equals to 2x squared minus the square root of x plus 5 all divided by the square root of x. Okay, now remember from algebra, when we have terms, right, which are all over one denominator, okay, you can give each of those terms, right, the same denominator, their own denominator basically. And how do you know that you have terms? Well, you can see that you have plus and minus signs, right, in between your expressions, right, and that's what qualifies the fact that you have terms, right. Your expression is made up of 3 terms. Okay, so we're going to have y. Okay, we're still going to write y because we're still manipulating. So we have y is equals to 2x squared divided by the square root of x minus the square root of x divided by the square root of x, right, plus 5 divided by the square root of x. Okay, so that's just giving each term its own denominator. Okay, right, now once we've done that, we can rewrite the square root of x as x to the exponent 1/2. Okay, so we're going to have 2 times x squared divided by x to the exponent 1/2, right. This is minus, well, the square root of x over the square root of x is simply just 1, right. Then we have plus 5 divided by x to the exponent 1/2. Okay, now we can bring that x to the exponent 1/2 to the top so that we can work with it. So we're going to have 2 times x squared times x to the exponent minus 1/2, right. I'm going to write the last term first, so I'm going to write plus 5 times x to the exponent 1/2, okay, and minus 1. Okay, now we are ready to apply the power rule. Okay, so all right, before that, let's just apply the law of exponents, right, to our first term. So this is 2, right, the bases are the same, so we need to add the exponents. So that's 2 plus negative 1/2, right, which is the exponent of 3 over 2, right. This is plus 5 times x to the negative 1/2 minus 1. Okay, now we are ready to apply the power rule. So we're going to have 2 times 3 over 2, right, times x to the exponent 3 over 2 minus 1, right. This is plus minus 1/2 times 5 times x to the exponent minus 1/2 minus 1. Okay, and obviously the derivative of negative 1 is going to be 0. Okay, because that's a constant, right. Oh my gosh, I've already taken the derivative, so this is actually supposed to be dy by dx. Okay, you can actually say therefore, okay, for that step, right, then dy by dx, okay, is equals to, well, 2 times 3 over 2 is just 3. This is x to the exponent 1/2, right. Then we're going to have minus, that gives us 5 over 2, x to the exponent minus 1/2 minus 1. Okay, that leaves us with the exponent of negative 3 over 2. Okay, now it's just a matter of cleaning up. So dy by dx, okay, is equals to 3 times the square root of x, okay, minus 5 divided by 2, okay, times the square root of x cubed. Right, so that x to the exponent minus 3 over 2 first of all goes to the bottom, and it is x to the exponent 3 over 2, alright, and we know from the rules of Sear's that we can rewrite this as the square root, right? So the denominator goes to the side and becomes your radical, right, and the numerator drops down to be your exponent, okay. And that would be the derivative function of our last example. Okay, and that is it for how to take the derivative using the rules of differentiation. You can see that the only challenge that they really give to you is the fact that you need to be aware that you need to manipulate, right, your expression first before you can actually apply the power rule. You can only apply the power rule once your terms are in the form a times x to the exponent n. Okay, and that's it for today's video. See you next time.